Hello everyone. Today we'll see internal resistance, EMF and potential difference of the cell. Now, what is meant by electromotive force? The electromotive force is the maximum potential difference between two electrodes of the cell when no current is drawn from the cell, or it is the total work done by the cell to circulate unit positive charge throughout the circuit. Now we can compare electromotive force and potential difference. The EMF is the maximum potential difference between two electrodes of the cell when no current is drawn from the cell, that is, when the circuit is open, while the potential difference is the difference of potentials between any two points in a closed circuit. The EMF of a cell is independent of the resistance of the circuit, while the potential difference is proportional to the resistance between the given points. The term EMF is used only for the source of EMF, and the potential difference is measured between any two points of the circuit. It is greater, that is, the electromotive force is greater than the potential difference between any two points in a circuit. However, the potential difference is greater than EMF when the cell is being charged. Now let us see what is meant by internal resistance of a cell. Generally, the resistance means the opposition offered by a conductor to the flow of current to the circuit. Similarly, the internal resistance of a cell is defined as the opposition offered by the electrolyte to the cell to the flow of electric current through it is called the internal resistance of the cell. Now we'll see what are the factors on which the internal resistance of the cell depends. Initially, the internal resistance of a cell depends upon separation between the two electrodes which are dipped in electrolytes. Larger the separation between the electrodes of the cell, more the length of the electrolyte through which the current has to flow, and consequently a higher value of internal resistance. That is, when we increase the distance or separation between two electrodes in a cell, the internal resistance decreases. It also depends on the conductivity of electrolyte. Greater the value of conductivity of electrolyte, lesser is the internal resistance of the cell. That is, internal resistance depends on the nature of electrolyte. The internal resistance of a cell is inversely proportional to the common area of the electrodes dipping in the electrolyte. The internal resistance of a cell depends on the nature of electrodes. Here we consider a cell having EMF E and internal resistance R. An external resistance R is connected across a cell. Let I be the current flowing through the circuit. Small v be the potential difference across internal resistance. Capital V be the potential difference across the external resistance R. Now by applying Kirchhoff's voltage law for a given loop, we state that the sum of EMF in a closed network is equal to sum of potential difference across the network. The sum of potential difference means the sum of product of current and resistance. In this case, E be the EMF of a cell, which is equal to the potential difference across the external resistance and potential difference across the internal resistance. The potential difference is given as product of current and resistance. When we solve this, we can get the value of I as the ratio of EMF to the sum of external resistance and internal resistance, and this relation is known as circuit equation. Now let us see what is meant by internal resistance and how it is calculated in terms of EMF of a cell, potential difference and external resistance. Here we consider a cell having EMF E and internal resistance R. An external resistance capital R is connected across the cell. I be the current flowing through the combination and V be the potential difference across the external resistance. By applying Kirchhoff's voltage law, we can get EMF is equal to sum of potential difference across external and internal resistances. By simplifying, we'll get the relation for internal resistance as E by V minus 1 into external resistance. Now we can determine the internal resistance of a cell by using voltmeter method. Here we consider a cell having EMF E and internal resistance R. Across this combination, we'll connect one key and external resistance box. To measure the potential across the cell, we'll connect an voltmeter across the cell. Initially, we'll keep the key open, that is, there is no any current is flowing through the circuit. That time the EMF is measured by using voltmeter. In the next case, we'll close the key, and when we close the key, the current will pass through the circuit, and the same time we'll measure the potential difference by using voltmeter, which is connected in parallel with cell. Now we'll see the combination of cells. First, the cells are in series. When the cells are said to be connected in series, the cells are connected in series when they are joined end to end so that the same quantity of electricity must flow through each cell. Here we consider three identical cells having EMF E and internal resistance R. These three identical cells are connected in series and an external resistance R is connected across the combination. Let I be the current flowing through the series combination of the cells, while V be the potential difference across the external resistance. In the series combination of cells, the EMF of the battery is the sum of individual EMFs. The current in each cell is the same and it is identical with the current in the entire arrangement. In this case, the total internal resistance of a battery or cell is the sum of individual internal resistances. In series combination of cells, the total EMF of the battery is equal to product of number of identical cells and EMF of each cell. And the total internal resistance of the battery is equal to product of total number of identical cells connected in series and internal resistance of each cell. Therefore, the total resistance of the circuit is equal to sum of total internal resistance of the cell and external resistance connected across the combination. The current flowing through the combination is given by the ratio of total EMF of the battery to the sum of total internal resistance and external resistance. In case of series combination of cells, if the external resistance is less than the total internal resistance of the battery, then the current is given by the ratio of EMF to the internal resistance of each cell. And if the total internal resistance of the battery is less than external resistance, then current flowing through the combination is given by N into ratio of EMF of each cell to the external resistance connected across the combination. We can conclude for the series combination that when internal resistance is negligible in comparison to the external resistance, the cells are connected in series to get maximum current. Now let us see the parallel combination of cells. When the cells are said to be connected in parallel, the cells are said to be connected in parallel when they are joined positive to positive and negative to negative such that the current is divided between the cells. Here we consider three identical cells having EMF E and internal resistance R connected in parallel such that the positive terminal of each cell is connected at single point while the negative terminal of each cell is connected at single point. Let R be the external resistance connected across the combination and I be the current flowing through the combination. In case of parallel combination of cell, the EMF of the battery is the same as that of a single cell. The current in the external circuit is divided equally among the cells when all the cells are identical. The reciprocal of the total internal resistance is the sum of reciprocal of the individual internal resistances. In case of parallel combination of cells, the total EMF of the battery or cell is equal to EMF of each cell. Total internal resistance of the cell or battery is equal to ratio of internal resistance of each cell to the total number of identical cells connected in parallel. And the total resistance of the circuit is given by total internal resistance of the battery and external resistance connected across the combination. The current flowing through the parallel combination of cells is given by the ratio of product of total number of identical cells and EMF of each cell to the total resistance across the combination, that is NR plus R. In case of parallel combination of cells, when the external resistance is less than total internal resistance of the battery, that time current flowing through the combination is N times the ratio of EMF of each cell to the internal resistance of each cell. And if the total internal resistance of the battery is less than external resistance, then the current flowing through the combination is the ratio of EMF of each cell to the external resistance. We can make the conclusion here: when an external resistance is negligible in comparison to the internal resistance, then the cells are connected in parallel to get maximum current.